Okay, this video I want to talk about protein structure. Okay, protein structure comes in 4 different forms: primary, secondary, tertiary, and quaternary. Starting with primary structure, and this is a really good image right from Khan Academy. Primary structure sequence is a sequence of a chain of amino acids. Okay, so with the primary structure, it is specifically the sequence of amino acids. Yes, they're held together by peptide bonds. That is not the primary structure. The primary structure is the order of the amino acids. So if I had amino acids 1, 2, 3, 4, 5, 6, that's my primary structure. Okay, let's say that's what it is. And if I change it up to 1, 4, 5, 2, 6, 3, I just changed my primary structure. Okay, I'm using numbers instead of amino acids, but you get the point. If I change the order, I'm changing the primary structure. Okay. For secondary structure, okay, that is our beta plated sheets and alpha helixes. Okay, so the primary structure can kind of wrap up into one of those structures. So it could either turn to alpha helices or beta plated sheets. There are very specific, there's a very specific way that each protein is going to fold. It's kind of incorporated into its primary structure. So it knows which one it's going to do. It's not really random. Okay, so these beta pleated sheets, they look like this, as you can see. And then alpha helices look like a helix. Okay, and they have very specific bonds. The image says secondary protein structure as hydrogen bonding of the peptide backbone causes the amino acids to fold in a repeated pattern. I really want to emphasize and highlight that it is hydrogen bonding of the peptide backbone. Okay, so the backbone made up of carboxylic acid and amine groups are hydrogen bonding with each other. Okay, so if I have carboxylic acid there and an amine group over there, there's going to be hydrogen bonding in between. So across, those parallel lines, there's going to be hydrogen bonding between the backbones specifically. Okay, I really, really want to emphasize that. Okay, something I want to emphasize also, and first off, the same thing happens with alpha helices, backbone interactions, backbone hydrogen bonding, just like that. Okay, I want to emphasize a couple specific amino acids, kind of going back. You may have noticed in my last video that I had glycine and proline written down. I didn't say anything about it, but I do want to make a note of it now. Those are both important amino acids in beta plated sheet structure. Proline and glycine are very rigid, very inflexible, and they can cause kinks in the beta sheets. Okay, so when I say kink, it's creating an acute angle. So if we were to have proline right here at this turn, that's very useful. That's what creates that turn. Okay, it kinks the amino acids, kinks that structure, and creates that turn. So it's very, very useful there. Same with glycine. Glycine can do the same job. Okay, so both of those amino acids are very important for that function. However, if there was some kind of mutation or accidentally proline got put right in the middle, it got put right in the middle of one of the parallel lines there on the beta sheet, that's not good because it's going to create a kink anyways, and it's going to turn it early, and it's going to misfold the protein entirely, or at least at the beta sheet, which is going to cause problems. So proline and glycine are useful in their specific locations. However, they're very damaging in wrong locations. Same thing if we had them in alpha helixes, then that's going to cause issues. Okay, we do not want those in their bad positions. We want them in their good positions. Okay, so that's our secondary structures. Our tertiary structure. Tertiary structure, three-dimensional folding pattern of protein due to side chain interactions. So as you can see in the image, it's just a big globular form. So a bunch of beta sheets, a bunch of alpha helixes get mashed together. So that's exactly what's happening, and it's creating, that globular structure. And that globular structure is able to be held together, not by backbone interactions. So once again, secondary is backbone, tertiary is side chain interactions. Okay, so I'm going to make a list of those. Side chain interactions, come on, please. Oh my goodness. interactions. Just going to make a quick list of them. Okay, so yes, we have hydrogen bonds. We have charged amino acids that may create ionic bonds. Okay, we also have nonpolar amino acids which might create van der Waals, also known as London dispersion forces. Okay, we might also see some other non-covalent bonds such as dipole interactions. Dipole interactions is an umbrella term for a lot of things. We'll get into those in the future. Whoops. And then the last possible one are disulfide bonds, which speak for themselves. It's just two sulfurs creating a disulfide bond. These we don't see as often in tertiary structure. They're still possible. They're covalent. They're actually very important for quaternary structure, which we'll get into. I'd say the most common ones for tertiary structure, probably hydrogen bonding, probably van der Waals, and then ionic bonds and dipole interactions, but mostly hydrogen bonds and van der Waals. Okay, the other ones are all still possible. Those are all our side chain interactions, so beware of those for tertiary structure. Quaternary structure. Quaternary structure. Protein consisting of more than one amino acid side chain. That's an incorrect explanation of it. Don't look at that. So quaternary structure is when you have multiple tertiary structures. So one tertiary structure might be this blob, this globular structure. Okay, if I were to put another structure next to it and link them, now it's quaternary structure. Okay. So each globular structure I would call a subunit. Okay, so those subunits together create quaternary structure, and we can see them as, you know, a group of two. We could see them a group of three. We could see them as a group of four, or many, many more. Could be a bunch of them. They all have specific names for them. This top one I would call a dimer. Okay, two subunits. Or another way to think about it is like one subunit would be called a monomer. This would also be its own monomer. So dimer would be two monomers. In this next structure down, you guessed it, trimer, three monomers. Then the last one, tetramer. Tetramer. 4 subunits. Okay. And it gets a little more complicated. Okay. As you can see, I did that on purpose, making the red and black, because we can have even more specific description of these quaternary structures. Okay. We could describe them as heterodimer. So we could describe them as hetero, or we could describe them as homodimer. Okay, so a heterodimer is what I gave an example of. It's got one type of subunit and a different type of subunit. Okay, so hetero meaning opposite. So they have opposite subunits together. And that's going to create a lot of differences. Well, I mean, they are just different. They could be different in properties, those subunits. The subunits could also be different in size, which is going to be useful to know in our next video. We'll get more into why that's important to know how they're described. Okay, a homodimer would be if those subunits are exactly the same. If they're exactly the same, they'd be called a homodimer. Okay, which is very important, like I said in the next video. So heterodimer, different subunits. Homodimer, same subunits. And you could also say hetero or homo trimer. You could say hetero or homo tetramer, so on and so forth. Okay, so just be aware of that. And the last thing, what type of bonds are important in quaternary structure? Okay, disulfide bonds. Oops, disulfide bonds. Okay, we already said they're covalent. Okay, they're very strong. They're very strong structures, and they're going to be useful in holding together these subunits. Okay, so these disulfide bonds are the only thing, at least that we need to know for the MCAT, that are holding together each of these subunits to create that quaternary structure. See you next video.